Rinig naman all the way to the back. Good. Okay. So, I'm going to preface this talk immediately, no? Kasi you may be led to believe when we say Rust for gaming, pag-uusapan natin how do you make games in Rust mismo. Pero medyo I'm going to turn this on your head a bit because we're going to be talking about game servers instead. Hindi tayo gagawin ng, let's say, doing Rust with Unity or doing Rust with Godot. We're going to talk about game servers, and in particular, we're going to be talking about highly concurrent game servers with the actor model. So, does this button work? Yes, it is. So hey guys, my name is Bas. I'm a full stack engineer in a Y Combinator backed startup based in the UK where we build some sort of sustainability as a service. If you think about this, it's essentially a platform where we can gather all of our charities, our customers, and all the stakeholders in a business, and we can get them streamlined nation pipeline for everyone. So essentially, we're building like a sustainability as a service kind of platform. So if you've been in the web development space for a while now, you've probably seen some of my articles at the top of Google's search rankings. Kanwari ako, I'm better known in the Dev2 community as some dude. So I'm pretty sure that you probably encountered some of these articles at some point. And yeah, feel free to contact me through any of these links here if you want to talk to me about programming or anything. No? I'd be glad to entertain you. So what are we going to talk about for today? Syempre, sa simula, we're going to talk about the problem that we're trying to solve to begin with and how Rust fits into the picture of online multiplayer. Because this is like one of the more rare topics that are discussed in game dev. In fact, it's kind of like taboo kasi parang ganun siya kahirap gawin. Anyway, so I'm going to explain all of these bullets eventually, no? Pero just to give you like a bird's eye view of where we're going, eventually there's going to be some kind of game demo here na may parang game server talaga tayo. So I'm going to request that everyone who has some mobile data or some internet access right now, i-connect nyo na ngayon as early as possible para hindi tayo nag-scramble later on. Okay, let's start with the problem of online multiplayer. If we start with web servers, yung use case niya usually is a very simple request-response model na parang meron kang stateless, short-lived requests, and then in return, you're going to get a response in return. And unfortunately, yung status quo natin for these kinds of web servers is that we have slow, delayed responses. Where have you seen a website that loads instantly, diba? Unless you have like some sort of progressive web app or something. I don't know if you're into that. Pero the point is, medyo normal yung idea na meron tayong one-shot request and then we're going to eventually respond to it 3 seconds later, right? It's a normal thing. Meanwhile, if we were in the game server industry, we're talking about performance constraints where we have to respond to requests within the window of a single frame in a game, or maybe 2 frames, 3 frames, or if you're a fighting game, for example, kanwari Street Fighter or Tekken, you can't really afford to miss too many frames. My point here is, whenever you're dealing with a game server, hindi na siya simpleng request-response lang as you would in a web server. In a game server, you have long-lived, stateful sessions, and that's not easy to do, kasi by the very reason that we have to keep track of state. And ayun, skipped frames really hurt the session. Okay, so one thing that they do have in common though, like let's say web servers and game servers, is the constraint of high I/O concurrency. So let's think about it for a bit, no? Since network operations are I/O bound, ibig sabihin nun, yung CPU mo, like 99% of the time, is actually just going to stand there and doing nothing while waiting for some database to respond. So like if you think about it, yung mga Intel Core natin ngayon, we have like 2.6 gigahertz processor. So it means like 2 billion cycles, and it can run that in 1 second. So ang dami mong CPU cycles na sayang dun. So ngayon, the key insights that we have for these concurrent systems, we don't have to wait for these I/O operations. We can do something else in the meantime. So in the context of a game server, for example, we could be servicing other requests, we could be computing physics, we could be computing game logic, and a whole bunch of other things in that 2.6 billion cycles that we do have. Parang sayang lang yung ginagawa natin kapag hinintay natin yung network or yung database for that. This was actually one of the key insights din pala ni Ryan Dahl. If you're familiar with Node.js, if you've been into the web development space for a while now, you probably used this technology at some point. Na-realize niya na although JavaScript is not really the fastest programming language out there, he realized that a lot of the server applications that we have in web servers don't actually need to be fast CPU-wise. We just need to be able to serve as many requests at the same time as much as possible. So even though JavaScript yung ginagamit natin sa Node.js, it's still a technology that can scale pretty far for your how many users, no? Kasi it can do things at the same time while waiting for other requests to finish. Just to summarize yung constraints ng game server natin. A game server has extreme constraints on high concurrency and low latency I/O bound operations, right? And as well as, since we're computing physics, kung kanwari physics yung ginagawa mong game, or whatever heavy compute that you need to do, it also has to be fast with CPU-bound operations. Fortunately for you, you are in a Rust conference right now, and what I'm going to show you right now is how we're going to use Rust to build highly concurrent game servers with the actor model. So we're going to go into what an actor model is eventually, pero first, unahin muna natin how do we even run asynchronous tasks in Rust. And for that, the ecosystem has the Tokio Runtime for that. So Tokio is the Rust ecosystem solution for highly concurrent I/O-bound systems. So for example, if you make a lot of network requests, if you go to the file system a lot, basically input-output systems, right? So yung ating Tokio Runtime is responsible for running what we call futures in Rust. A future is something that will eventually succeed or fail with some value. If you've dealt with JavaScript promises before, this is a very familiar concept. It's, for the sake of this talk, let's just say that they're equivalent. Pero may distinction yun between eager evaluation and lazy evaluation. No? Pero we're not going to go into that deep end. Here, we have what we call an async function in Rust. It kind of looks very familiar to an async function in JavaScript. And yung una natin ginagawa dito is that we have some HTTP client, we're going to make some network request somewhere, and yung gusto natin gawin is to get this URL from somewhere. And if you notice at these points, kapag sinabi nating .await, ibig sabihin nun, these are specific points in the function where it can pause. These are particular places where we're possibly going to wait for a long time. So we have to signal to the Rust compiler that don't expect the result immediately. This is the point where we can actually have someone else interrupt us, and this is where this is the part where we can have concurrency. So anyway, one of the key insights that we have from this design is that a future kind of looks like a state machine. So this is not really a computer science class, pero I just want to illustrate here from the beginning na parang meron tayong initial state na ginagawa sa ating future, and now we have a step 1 after we finish the await point, and then my step 2, and then we have a done once the request is ready. And believe it or not, when things get compiled down at the compiler level, this async function eventually becomes this enum over here. Sorry, nag-overlap ng konti yung text, but it's going to be an enum na meron tayong initial, step 1, step 2, and done. So we're going to get into this and why it's like designed this way. Pero just to show you yung overlap niya, just to show you the screen again, we have the step 1, and then we have the step 2, all in the same place. So if Rust compiles this into something that we call a future, this is essentially what it's going to look. It's going to be one huge state machine. So we're going to look at this in a very zoomed in level. Specifically, let's start with self-initial muna, no? So self-initial here now looks really familiar. This is like the first 2 lines of our function from earlier. And notably, wala siyang await, but we're actually going to pause specifically at the http.get line over here. Biglang nawala din yung .await, and we're going to store yung kanyang future value dito sa ating step 1 variant ng ating enum. And this is what's going to store the intermediate computation. So let's say, gumagamit ka ng Linux, for example, to send off your HTTP request, yung OS mo actually yung bahala sa pag-send ng request na yun. Pero as far as our Rust program is concerned, it's just going to wait for the OS to respond back to us. So in the meantime, let's store any information that's needed to remember that operation inside this future. So that's whatever is returned by http.get. And then yung trabaho na natin ngayon is to return poll pending, just to signal to Tokyo, kanwari, na hindi pa tayo tapos sa operation na to, and we can still keep going later on. The important thing to notice here is that yung self actually, we're trying to reassign it to a brand new state in our enum. And that's essentially what it means to be a state machine. Meron tayong different states, and we're transitioning them into different states whenever we're ready. So the next time that we call this function, yung mangyayari, mag-transition na tayo sa step 1. Hindi na tayo dun sa initial step. And ang gagawin natin dito is we're going to look at the future from earlier, and we're going to check if it's ready. So dito yun sa second line, for example. Medyo macro yan, so maraming magic na mangyayari dyan. But I'm not going to go into those details kasi I really just want to show you guys a high-level overview of how a future works. So ayan, once the future is ready, now we invoke yung response.collectBody dito sa baba. And that's the part where we start streaming in the bytes from this HTTP request. And notice again that since we've completed the future, we're going to proceed to step 2. And that's the part where we're going to open self again and store the intermediate state of our future from earlier. And of course, since we're not yet done with our function, we're going to return poll pending. Great. Step 2, it's the same thing. Meron kang future na store somewhere, and you're going to keep polling it until it's done. I mean, that's literally line number 3, no? So kapag tapos na yung future.poll na yan, we're going to reassign self to become done. And after that point, hindi na tayo poll pending, we're actually going to return a poll ready. And that's the final line that we have here, dun sa body.intoVec nung original function. And something that's like a very detail about this is that once we're in the done state, ang ginawa ko lang dito is we're going to panic. We're going to say na unreachable tong code na to because yung contract ng future sa Rust is that once they're complete, you don't really poll them again. So we kind of just panic here if ever it happens. It means may bug dun sa implementation natin. And that's not a bad thing to crash your program. In fact, really good thing that you crash in development versus crashing in production. So that's much better to deal with it right now. Okay, let's zoom out. That's what it looks like. But what I'm trying to tell you is that it's just one big fancy state machine. You go from one state to the next kapag natapos na yung async operation natin. But this begs the question, who's going to invoke yung poll function na to? Sino yung nagtatawag nung poll signature na yan? And yung sagot is, it's actually Tokyo. The Tokyo runtime will be responsible for running these futures to completion. So how that would look like is kind of how it's implemented as well in the JavaScript world. We have what we call an event loop. So whenever an asynchronous task gets enqueued, yung ginagawa ng Tokyo runtime is that it pulls the future until the next await point. And yung await point na yon is the place where we essentially pause state machine, right? And then for these asynchronous I/O operations, we kind of just go to sleep after that point. Parang while we're waiting for the operating system to give us a response, this task can go to sleep. And then once it's ready, the OS can wake up yung task na to, and we're going to put ourselves back into the event loop so that we can be polled again. No? And ulit-ulit lang yun hanggang matapos yung operation. You keep polling and you keep polling hanggang sa maging poll ready siya. So yeah, pretty basic in concept, no? So you have an async fn, and tuwing meron kang .await, that's essentially the point where you do a state transition and you pause the function's execution from that point. Okay, so in production though, or in practice, what we have is Tokyo runs a multi-threaded stealing executor. So it's basically, ibig sabihin nun, you have a whole bunch of tasks running everywhere, and then they can run across multiple threads. And even if you were single-threaded, the cool thing about it is that these tasks are multiplexed in the same thread. So parang even if you have sleeping tasks somewhere, you can just stow that away for now, and then you can start executing the next one that wants to be woken up. So even if you didn't have a multi-threaded thing happening, you can actually have concurrency anyway. And this is like exactly what we want for a game server. So we have a highly concurrent server with respect to IO-bound operations, and we have a fast programming language with respect to CPU-bound operations. you would want to apply some SIMD, for example, or some kind of other algorithmic optimizations. Okay, so how does Tokio achieve all of this? Dito na tayo papasok sa tinatawag nating actor model. So the natural way to develop your systems when using the Tokio runtime is using an actor model where each task, when I say task, that's your future essentially, we can think of them as some node in this graph right here. And interestingly, lahat ng mga nodes na yan, meron silang mga mailboxes. Yung bawat mailboxes na yan is a place where we can send and receive messages from each other. And essentially, yan lang yung goal ng ating system. You have a whole bunch of messages that pass from one actor to the next, and that's how you make them to each other. These messages are what we call, these messages are facilitated using message channels dun sa Tokio. We'll see that later. Pero if you're familiar with Go channels, it's a very similar concept as well. Okay, so as soon as an actor receives a message, yung trabaho niya is to process that message until completion, until it runs out of messages in its queue. And naturally, if you don't have anything in your box, the actor can just go to sleep. And in fact, if you don't have anything to do at all, everyone can just go to sleep, diba? So it's a very highly efficient system and a very highly parallelizable system as well. Because now you don't have to care about where your message comes from. As long as you keep processing and servicing these requests, you can spawn as many of these actors as you want and do as much work as you want. Okay. So how do we do this in Tokio? Meron tayong tinatawag na Tokio spawn. That's the way that we tasks. It's kind of like spawning a new thread where you have a separate branch of execution at that point that happens in parallel. Concurrently is the more correct term, ano? Pero the thing is, it's not like stood thread spawn, kasi Tokio's tasks are more lightweight than OS threads. In fact, they're not threads at all. They're just tasks. They're futures, right? So if you're familiar with the concept of green threads or virtualized threads in Go, it's practically the same concept, no? So this abstraction here lets multiplex tasks even on a single thread. Imagine if you have multiple threads na, suddenly your 8-core CPU can handle a whole bunch of requests at the same time concurrently, right? Pretty cool. So how would that look like? So we have a loop here. Kanwari meron tayong TCP listener, and yung trabaho niya lang is to keep looping until it connects to somebody. So ang ginagawa natin dito is when we receive a stream, we're going to throw that stream into the Tokio spawn, and then siya na yung bahala sa pag-process ng message na yan, which is yung stream that we moved into there. Meanwhile, yung main actor natin goes here sa bottom of the loop and goes back to the top where it's going to accept new connections. And at the same time, our worker actor here will continue processing these bytes. So the interesting thing about this is suddenly we can do two things at the same time, where we can wait for new connections and we can wait for incoming bytes as many times as we need, right? So pretty cool. Now, we've mentioned earlier na meron tayong mailboxes sa actor model natin. Let's talk about how we implement that with Tokio. So in Tokio, we have 4 types of channels. Probably there's going to be more in the future, no? But the basic ones are your one-shot channel. As you suggest, we only have one message that can pass through. We have multi-producer single consumer channels, or MPSC, because I don't want to keep saying that, where you have like a many style of connection. And then you have a broadcast channel where you can have a many-to-many kind of communication. And you have a watcher channel, which is only responsible for notifying you whenever a certain value gets modified. But we're going to specifically focus on 2 of these kasi yun yung parang pinaka-relevant sa game servers. Specifically, the broadcast channel and the MPSC channels. If you notice, yung ating many-to-many use case sa ating broadcast channel can be simplified as a one-to-many problem. And suddenly, now we have a way to broadcast a system message to multiple sockets or TCP streams if you're talking to a different user. And then yung MPSC channel na rin is some way for us to take multiple messages from a whole bunch of clients and stuff them into some centralized hub. Diyan papasok yung use case for MPSC. And if we zoom out of this network topology, it kind of looks like the classic server authoritative model for all game servers out there. Sorry, not all, but most game servers out there. na meron kang centralized server that handles all the logic, and you have a whole bunch of clients that's talking to the same server. We can use broadcast channels and MPSC channels for that. Okay? So just to show you some common patterns dun sa actor model natin, let's say you wanted to do a request response model. Alice Ryle, the maintainer of Tokio herself, had this very nice talk, very convenient kasi I could just like take the slide, ano? Na a very common pattern that you see with actors is that you have some actor on the left na parang meron kang receiver channel for these commands, and you have ownership over this input-output resource. Let's say some network socket, some file system operation, and so on. Tapos on the right, some actor handle that's actually the sender of commands to that specific place. Cool thing is, kung gumamit ka ng MPSC channel dito, suddenly now you have the power to clone yung actor handle mo across multiple threads, and you can actually command the actor to do many things from multiple threads. So that's, you can imagine that's like a way to do a lot of players talking to the same game server. So how would that look like? Kanwari meron tayong struct message dito. We have the request, which is your payload, and then we're going to send them some kind of one-shot sender from to which they will send the response back to us. So in code, it kind of looks like this. So we're not going to look at the whole thing. We're going to look at the first part first, where we're going to create an MPSC channel for all the messages that are incoming. And then yung gagawin natin is we're going to spawn a worker actor that's going to loop through all of these requests, and we're going to send +1 back to the caller. That's it. Yun ang yung trabaho ng worker. A very simple actor. And then back to the main worker, like back to the main thread, ang gagawin natin is we're going to create a one-shot channel here, and then we're going to send the message with some 0 and yung sender half ng ating one-shot channel. And that's it. So for us to receive the response, we just have to say rx.await. And we're going to assert na 1 yan kasi nag-increment lang siya. The convenient thing here is though, kapag dinrop na natin yung requestor, and I've highlighted it in red for you to see na that's the same requestor that we've been using all throughout, this is a way to signal to the worker actor that no more jobs remaining for this queue. And yung gagawin lang natin at that point is to just like tear down the worker. So babalikan natin dito sa taas, yung loop na yan will just stop running, and it's going to gracefully shut down. So this kind of synchronization primitive where you can drop channels in and out is one way to synchronize state in your game protocol, and a very useful thing to consider when you're going to build your own game server. So, recap what we learned. Performance constraints of a web server and how it's different from a game server. We learned how a future is essentially a state machine under the hood. We also learned that a future is essentially just a state machine, and the fact that it's a state machine lets us pause the execution at await points throughout the function, and that lets Tokio, which is multi-threaded work-stealing runtime, for us to be able to run as many actors in parallel and concurrently as much as possible. And then, syempre, we learned that the architecture makes all of this possible and all of this ergonomic, which is the actor model, and we also have message passing with Tokio Channels. So that said, no, thank you to everyone for listening.